So I do have the pleasure to introduce Catherine Moyes from University of Oxford. She is serving as a research associate. Catherine is a co-founder of Atlas of Baseline Risk Assessment for Infectious Diseases. She led a Malaria Atlas project's work on insecticide resistance on malaria vectors. Her group also developed methods for predicting spatial temporal variations in resistance and investigating associations with potential drivers of selection. Catherine talks today is about geospatial patterns of insecticide resistance. Aklilu's talk was mainly focusing on PMI, based on PMI data and PMI countries, while Catherine's talk would be of global in scope. So, Catherine.
Thank you. The work I'm going to talk about today is a collaboration between the Malaria Atlas Project and Liverpool School of Tropical Medicine. And the aim of our project is that we want to characterize spatial temporal patterns in insecticide resistance in order to use these to look at the relationship, if any, between insecticide resistance and residual variation in malaria transmission. Specifically, we're interested in the residual variation in Plasmodium falciparum infection prevalence in Africa. So in order to do this, we need to understand variation in insecticide resistance across Africa for the 15 years from 2000 to 2015. And to do that, the data we have available to us on insecticide resistance overlaps with the previous talk. It's the WHO susceptibility bioassays. And these bioassays weren't developed for this kind of work. So they're developed as an early warning system to look for signs of resistance, specifically prevalence of resistance to a diagnostic dose in the early stages. And as we saw in the last talk, people are most interested in the variation around the 95, 97, 100% mortality thresholds. But we actually have the full data available to us from 0 to 100%. These bioassays are notoriously noisy. So they use live mosquitoes and conditions may vary, sample sizes may be small. So we set out to see, first of all, whether we could actually characterize spatial and temporal trends in insecticide resistance using this data, and then whether this data can be used to then look at the residual variation in malaria transmission. So if I go back actually, while we're still on this slide, we've got data for the 4 main insecticides used in vector control, and principally for the pyrethroids, which are the main insecticide used. And if you look at any of these maps, you can see the data is highly clustered in space, and we know that if you zoom in at any different spatial scale, that clustering still exists, and there is also sampling bias through time. So we needed to have a method that addressed that. So we needed a lot of data through time and space in Africa, and we needed to address the sampling biases in that data. Zooming down into the pyrethroids a little bit more, this is the volume of data that we have for prevalence of pyrethroid resistance in the Anopheles gambiae species complex. And you can see we've got a decent spread of data across countries in Africa and through the years that we're interested in. So our next step, Penny Hancock in my group developed a geostatistical model to look at the spatial and temporal trends in this data. And using a geostatistical model, it relies heavily on spatial dependence, so it can take account of the sampling biases that we see in the data, but we do need a lot of data to provide estimates of resistance. And for the first stage of this work, Penny concentrated on the spatial temporal random effects and the unstructured noise in the data, but the modelling framework does allow us to use covariates as well, so factors that might explain some of the variation in insecticide resistance. So in the first stage of this work, we didn't incorporate covariates, but the modelling framework does allow us to. And here we have the first results from this work. So the paler values are 100% mortality, so that's susceptibility to the insecticide, and then the darker, bluer, more intense colours are going down to 0% mortality, so high prevalence of resistance. And I'm going to run through this slide twice because what we have here is 2-year time bins for West and East Africa. So if I run this again. And you can see that using the bioassay data, we are able to pick up patterns in resistance in both time and space. And it's going to run through the second time now, so you can see resistance arising first in West Africa and then spreading through East Africa later. So that was a good start. However, what we're showing on these maps here are, of course, estimates. They are our mean predictions from a posterior distribution of values. And there are uncertainty in those estimates, and it's important to consider that uncertainty. So what we have here in the bottom on the left of this slide and on the far right are the credible intervals for the mean values that I just showed you for the year range 2014 to 2015. And where the colours are more intense, we have smaller credible intervals and therefore more certainty about our mean values for insecticide resistance in those locations. And where the colours are less intense, where we have a paler colour, then that's where the credible intervals are large and we have less certainty. And they're largely associated with the areas where we don't have much data. So we want to try and improve our predictions in those places. And we've got 4 different approaches to doing that. So the first approach we took is that we know that there are mechanisms of resistance that cross between insecticides. So within the pyrethroids, one mechanism of resistance for a particular pyrethroid might also confer resistance to another pyrethroid. So we wanted to see whether we can utilize this to leverage data from one insecticide to improve our predictions for another one. So the next stage of Penny's work is that she took our model and she developed a joint model using 2 insecticides, or 3 insecticides, or 4, and she compared the performance of these, so models for a single insecticide or using 2, 3, 4, to see which performed best for 4 different insecticides. And in all 4 cases, what she found was the model performed best when we incorporated 2 insecticides into the model, and the specific pairs are these. So we've got, when we modeled deltamethrin, that model performed best when we incorporated permethrin data. When we modeled permethrin, that performed best when we incorporated deltamethrin. Lambda-cylohethrin performed best when we incorporated deltamethrin. So these 3 pairs are all pairs of pyrethroids, but we also found the same thing across organochlorines and pyrethroids. So the DDT model performed best when we incorporated permethrin in that model. So we're already improving our predictions here, and it's also quite interesting to see the relationships that come out of this. So what these plots are showing are the model outputs for the prevalence of resistance to a diagnostic dose for each of these insecticides. And of course, these values are estimates, so again, they come with uncertainty. So the dots that are a more intense colour in these plots are more certain, and those that have faded out are less certain. At the moment, we're doing a piece of work to see whether the model structure that we selected has influenced the shape of the curves that you see here. If that's not the case, then it's quite interesting to see that it looks like either some of the insecticides you get higher prevalence of resistance compared to others, or perhaps there's something going on with the calibration of the diagnostic doses for the different insecticides. And it was also reassuring to see we modelled East Africa and West Africa data entirely separately, and we were finding the same patterns and the same curves with both. So that was the first step that we took to improve our predictions of insecticide resistance. Because it looked like there was some relationships happening here and something useful going on with the phenotypic resistance to these different insecticides, we're also interested to see whether the markers for specific mechanisms were also useful. And of course, we know from previous work that metabolic resistance confers higher levels of resistance. However, we don't have markers for metabolic resistance where we have data for those across Africa across our 15 years. So we don't have the data to incorporate into this kind of model for metabolic resistance. But we do have data on KDR. And we know, again, from previous studies, that KDR isn't associated with such high levels of resistance. So we weren't sure what we'd find. And when we took KDR allele frequencies and compared those to the results of the individual bioassay that the sample of mosquitoes that was tested for the KDR alleles. So when we had paired results and we compared those, we didn't see any kind of strong relationship. But we carried on and had a little bit look further. And when we took the allele frequencies, in this case the frequency of the wild type gene, so the susceptible allele, and compared them to our mean predictions for an area, we found that it looks like there is a relationship. So at the moment we are still cleaning this data, adding to this data, and we need to formally analyze it. So this is a very simple visualization, but it looks like there may be something going on. And even if KDR isn't causal for insecticide resistance, it may be coincident with it, and it may have some value in predicting the mean or the expected level of resistance or prevalence of resistance in an area. And of course, it's important here to consider these mechanisms within individual species because you get variation there. And I'm going to come back to the issue of species shortly. But before I wrap up on the differences and similarities between insecticides and leveraging those, I just want to mention that, of course, I've talked about pyrethroids and a little bit about cross-resistance between pyrethroids and DDT, but we are interested as well in carbamates and, more importantly, organophosphates. However, we do have some issues here. As you can see in these plots, we have much less data for the organophosphates and the carbamates, especially when you consider the data we have for an individual insecticide within those. And what you can also see for the organophosphates is that we have much less variation in the prevalence of resistance. So if we're interested in the bioassay as an early warning system and the WHO thresholds at the high levels of mortality, then you can see signs of resistance in this data set. But we're interested in the full variation from 0 to 100%. And we're just not seeing as much variation for the organophosphates, so it's harder to model variation that's not there. So that's where we are with cross-resistance and individual insecticides. We're also interested in individual species. We know from studies at particular locations from field studies that where they've found differences among species and species within the Gambii complex in levels of insecticide resistance. And if we look across Africa at our data set here, what we've got is the mean values for the prevalence of resistance or mortality for 3 time bins for 3 species, Arabiensis, Clusii, and Gambii. And it looks at first glance as if there's something going on here. It looks as if there's a trend for decreased mortality and increased resistance for all 3 species. And it looks as if we've got more resistance in Gambii than Clusii, for example, and more in Clusii than Arabiensis. However, we've included the information on the right-hand side of this table to just highlight the point that these data weren't collected at all the same times and places. So the data in the first time period was not collected from the same countries as the second or the third time periods. And the places sampled for the 3 different species don't match either. So we don't actually know whether these apparent trends in the data are real or whether they're just a result of sampling bias. So ideally, we'd like to do something similar to the approach we took for the insecticides, looking at the differences between species, but also whether they have similar patterns of resistance that we can leverage when modeling them. However, we do have a roadblock here because the bioassay data that we have, every single bioassay result is linked to an individual insecticide. So our full database can be used when we're looking at individual insecticides. The same isn't true for species. So the bioassay records are often just linked to a species complex. And of almost 9,000 records that we have for the Anopheles gambii species complex, only 842 are actually linked to, for example, Arabiensis, the species we have most data for. And for that, 842 sounds like a decent sample size, but of course that's split amongst 4 classes of insecticide and multiple insecticides within each class, and it's also spread across Africa and from 2000 to 2015. So all of a sudden that looks like a more restricted data set. However, we still think species are important, so we're looking at different approaches. And one of those that we're considering is to model the relative abundance of sibling species within the Gambii complex. So we have quite a lot of data on this. The data that I'm showing up on this slide here is partway through the database, so we have a bit more. And there's a good relationship between environmental factors and the relative abundance of these species, especially when you take into account their respective ranges. So it's possible that we could model the species composition at each location and then link that species composition with our bioassay results. So that's not as good as having the real species composition that went into the bioassay, and it's a model prediction, so it comes with a level of uncertainty that would need to be propagated through the model. But it's one approach that we think we might be able to take, and we'll be testing in the coming months. So coming back to our modelling framework, I mentioned that our first part of our work, we didn't incorporate any covariates, so the kind of factors that we think might be linked to variation in insecticide resistance and help us to predict it in areas where we don't know what it is. But we do want to incorporate those. And so just to talk a little bit about where we're going next with the model. In the past, when the Malaria Atlas project has modelled the distribution of malaria vectors, or when it's looked at Plasmodium falciparum infection prevalence itself, we've found good, strong relationships with factors such as temperature and moisture, as you would expect. So they've helped improve our predictions. However, we don't know whether those kind of factors are actually linked to insecticide resistance at all, although we will have the ability to test that within our modelling framework. The factors, the variables that we think are more likely to be interesting and useful, as you would expect, 3 sources of potential drivers of selection. So insecticide-treated bed nets, indoor residual spraying, and the agricultural use of pesticides. So the 3 mechanisms through which we expect mosquitoes to come into contact with insecticides and hence develop resistance. For insecticide-treated bed nets, we've already done some work triangulating 3 data sources. So survey data on whether someone slept underneath a bed net, country data on their distribution within country of bed nets, and manufacturer data on their distribution of bed nets to countries. We also have some more coarse data for indoor residual spraying, but there is no data for all locations in Africa on the use of pesticides or pesticide residues in the environment. So we're going to have to take a slightly different approach there. I'm running out of time, so I'm going to skip slightly over this. But we do think that the agricultural use of pesticides may be important, and there's already evidence out there that in places where pesticides are used in West Africa, then resistance arises. And we are going to try and incorporate various factors linked to pesticides in our insecticide resistance model. Finally, what we want to do last of all is to take our best predictions and our best characterization of the spatial and temporal trends in insecticide resistance and compare them to the trends that we see for variation in Plasmodium falciparum infection prevalence. Specifically, this is some work from a couple of years ago led by Sam Bart and Pete Gething in the Malaria Atlas project that looked at attributing variation in infection prevalence to insecticide-treated bed nets, indoor residual spraying, and ACTs. And this accounted for a fair amount of the variation, but not all of it. So we want to see whether insecticide resistance helps to explain the discrepancies when we look at what we expect to see from these 3 interventions and what we actually see in terms of Plasmodium falciparum infection prevalence. So this sums up the talk so far, and I'll quickly skim over it just to say a huge thank you. The data we use comes from a large amount of published studies and also an awful lot of unpublished data. So thank you to everyone who contributed that.
So great work, great presentation. So we do have a few minutes to take 2 questions. So I would like to ask the people who would be asking to tell us your name and affiliations when asking questions. Thank you.
So thanks, Derajay. Michael McDonald, formerly with PMI. Question about selection pressure, especially for pyramidphos methyl. It's obviously disturbing to see this happen. Pyramidphos methyl is a very common insecticide used for stored grain products. I can remember in Malawi seeing packets of 1% pyramidphos methyl distributed by Ministry of Agriculture. Not sure if that was a USAID Feed the Future project, but it's very common for stored grain. It's common for ear tags for cattle, which may have something to do with arabiensis. And it's very common for cut flowers fumigation. So I'm wondering, in our work, are we looking at household use of pyramidphos methyl products in other areas besides what we're putting on the wall?
Yeah, so not specifically at the moment. So the agricultural use of pesticides side of things is more focused on spraying of crops at the moment, and we've got data available for crop coverage and yields and various other factors. We don't have good data for things like storage of grains.
Well, this is household use, so
Yeah.
it's possible when the spray operator goes in just to see what other insecticides are in the house.
Yeah.
And-
No, that data would be great, and anything we can, we will incorporate.
Any other question? Okay.
Hi, Rachel Sippy, University of Wisconsin. I was wondering, given the variety of data you're using, obviously they will have been collected over lots of different temporal and spatial scales. Can you speak to how the model chooses to make use of that data? Like, are you aggregating or something like that? Thank you.
So we actually, our inclusion criteria into the model, we don't put in data that covers large spatial scales or large temporal ones. So our resolution for the data has to be a sample of mosquitoes that were collected within an area of 5 by 5 kilometers. So if we have data where people have sampled from, say, 5 sites within a district, then we don't try and assign specific coordinates to that. And the same with the temporal data. So within a year or within a 12-month period is the scale that we use.
Thank you.
Okay. Thank you. Thank you, Catherine.